Dear ECTC 2020 attendee, we would like to welcome you to session 44, titled Optoelectronics, Flex and Emerging Techniques, organized by the Interactive Presentation Subcommittee. The session co-chairs for this session are Rao Bonda from Amcor Technology and Jeffrey Lee from Integrated Service Technology. This session has 8 talks. The first talk is titled Controls on the Transport of Particles Cells in Deterministic Lateral Displacement via Symmetric Airfoil with Angle of Attacks, presented by Kaukab Ahsan from Washington State University. Our second talk is titled Optical Platform for Highly Precise Optical Components, presented by Sebastian Bench from Leibniz University, Hanover. Our third talk is titled A Design and Fabrication of Transmission Line for ESIFO in Millimeter Wave Applications, presented by Shengjuan Zhu from Tsinghua University. The fourth talk is titled Low Power SoC Based on High Density MIM Capacitor for Beyond More Era by Robust Power Integrity Achievement, presented by Jisoo Huang from Samsung Electronics Company. Our fifth talk is titled Design of Optical Transmitter Module for O-band Silicon Photonic Engine, presented by Xian Wu from National Kaohsiung University of Science and Technology. Our sixth talk is titled Flexible Batteries Under Dynamic Folding Flex to Install with Varying C rates and temperatures, presented by Pradeep Lal from Auburn University. Our seventh talk is titled An Embedded SiC Model with Using NMPB Interconnection for Chevron-Shaped Copper lead and chip electrodes, presented by Naoki Fukui from Waseda University. Our eighth and the last one is titled Design, Fabrication, and Characterization of a Q-band patch antenna integrated on stacked interposers, presented by Yunhang Sun from Peking University Shenzhen Graduate School. We know you will find it extremely valuable to learn about the cutting-edge developments covered in these talks and enjoy the talks as much as we did. Thank you for attending.
Hello, my name is Sebastian Bengsch, and I'd like to welcome you to my talk about the optical platform for highly precise optical components. I'm from the Institute of Microproduction Technology from the Leibniz University in Germany. I want to give you a quick overview of the content of this presentation. I will start with the motivation, which is followed by the introduction. This is followed by the concept of the injection molded wafer, the manufacturing of the injection molded wafer, the concept of the pocket and the laser diode. I will give you an overview about the concept of our waveguides and the manufacturing of our waveguides, as well as the concept and the manufacturing of the gratings. In the end, I will give you a short summary and an outlook. The motivation. I work for the Cluster of Excellence Phoenix D, Photonics, Optics and Engineering Innovation across disciplines, which is funded by the DFG, German Research Foundation. The topic in this funded project is the system integration of optical precision components. We all know that fiber optics are already in the focus of modern telecommunication infrastructure. Therefore, we want to use this concept to create integrated optical fibers inside a polymer platform. There's a big research potential for applications and a lot of production possibilities of integrated optical waveguides. We want to use the advantages due to the injection molding properties in this concept. The injection molding has a lot of benefits. The benefits are a cost-effective mass production, high reproducibility, and individual complex component geometries. The figure on the right side shows a concept of integrated optical systems, which is presented in the Phoenix D. All right, let's look at the demonstrator. The concept shows a substrate for the optical infrastructure. In the middle, you can see a cavity, which is the waveguide channel, and close to the waveguide channel there can be gratings applied on the substrate to become the light, or to get the light from vertical into horizontal waveguide structure. We can have also OLEDs or LED active components, which are bare-diced or housed, as well as photodiodes and other optical components like lenses and so on. So we will focus on the substrate in this presentation. We had the idea that we use the manufacturing process of injection molding for the substrate platform. The material is supposed to be a polymer, a thermoplast, which is injection molded in to the desired shape of a 4-inch substrate. In the center picture, you can see the master tool of the injection mold device at the institute. We have in the center of the injection mold a core, and on this core there is a injection mold inlay. This mold inlay is fabricated in-house at the institute using common lithography and electroplating processes. We use steel as a substrate. We have different sorts of steel. For example, low alloy steels and stainless steels. The low alloy steels will be polished in-house using CMP. The next steps are common lithography and electroplating process steps to create nickel electroplated structures, which will imprint it into the injection mold specimen. When we look at our steel substrate wafers, We have managed to create optical structures like waveguides, which can be seen in the top left picture. This is an actual mold inlay, which is fabricated in-house. The mold inlay can be seen on the right picture on the top, which is inserted in the injection mold machine at the institute. For our concept, we use the thermoplast material, which is laser direct structurable. It is a polyether-ether ketone, also called PEEK, supplied by the company Ensinger. This is a material which is also used in terms of MID, mold interconnected devices. The material is highly chemical inert and has a high temperature stability of about 300 degrees Celsius. The injection molding is a not easy process in this case. We have a lot of struggles to handle, or challenges, which are, for example, the planarity. The planarity of the substrate is a big issue. Therefore, we had to work on the material parameters, or on the injection mold parameters. And after several DOEs, we could create planar and very good specimen, which have a high surface planarity. The next step was the evaluation of the surface. In the first step, we evaluated the surface of the mold in terms of the electroplated structures, because they determine the quality of our plastic specimen and of our optical components in the end. If we look on the left table, or left graph, we can see different steel substrates, the C45 and the V2A. We have different layer heights of the electroplated structures, starting by 4.5 micrometers and up to 75 micrometers. We looked at the surface roughness, and the surface roughness is in terms of the smaller structures below 20 millimeter in average. This surface roughness is sufficient for optical passive components we address in this research topic. On the right side, you can see a confocal image of an optical waveguide structure of our master mold. You can see it has a high surface quality. If we look at the surface evaluation of the plastic parts, we can see that we have increase of the surface roughness, which is very low. We're in average concerning our best structures of about 30 nanometer roughness. We can see that there was a roughness difference in terms of the temperature of the mold. So at 130 degrees mold temperature, we can see a surface roughness of the desired 30 nanometers. On the right image, we can see a picture of the confocal microscopy as well. And you can see the channel of the waveguide. We measured all the channels inside on the bottom to see the surface quality of the waveguide top. We can see that we have an increase of the surface roughness in the side walls, which is determined by the injection mold process. All right, let's come to the concept of the pocket and the laser diode. If we look at our substrate in this picture, we can see a pocket. The pocket is for adjusting the laser diode towards the waveguide, which is inserted into the channel. The laser diode is contacted by laser direct structuring on top and on the bottom. The bottom connection is done with a via connection, vertical interconnect, which is performed by the laser direct structuring as well. If we look at the concept of the waveguides in further detail, we can see on the right side the process flow, where we can see the pre-structured PEEK substrate and a sidewall coating using PVD processes. The sidewall coating will be the cladding of our waveguide in this case. And you can see that the material which is chosen is a gold layer. The cavity will be filled using Dr. Blade spin coating processes with PMMA, and if desired, a top coating of gold can be applied onto the waveguide material. Why did we choose gold as a reflective cladding material? We use a laser diode in our project of about 950 nanometer wavelength. And if we look at the graph of the reflectance of surfaces of different materials, we can see, if we look at the gold, that a wavelength of 950 nanometers, we have a reflectance of about 99.4%. Regarding the optical attenuation, on a very small substrate, like a 4-inch substrate, the optical attenuation is only depending on the roughness of the surface in this case, and the reflectance of the gold can be neglected in this case, the attenuation regarding the reflectance. Therefore, only the roughness and the surface quality is the goal to reach. So we're looking at the manufacturing process right now. The manufacturing process, which can be seen on this slide, is the Dr. Blade process. The Dr. Blade process can be seen in the top picture. We created waveguide structures inside the cavity with better surface quality in comparison to the peak structures, which can be on the top, can be seen on the top and on the bottom. Waveguide diameters from 20 to 50 to 100 micrometers could be achieved. The UV hardening took place in about 7 seconds, and we could increase the surface roughness of the waveguide. Spin coating has been performed at 1000 RPM at our facilities. We can see very good surface quality of the waveguide material on the top and on the bottom picture. The bottom picture also shows the smallest diameter created, which has been 10 micrometers. Right, let's get to the gratings. The concept of the grating can be seen in this slide. The gratings can be applied on top of the waveguide using embossing tools, or the gratings can be applied directly on the mold inlay of our steel substrates to be addressed at the bottom side of the waveguide inside the channel. The manufacturing of the grating structures can be seen in this slide. The grating structures are created using electron beam lithography and the lift-off or IBE process. The gratings were produced on the top of the waveguide structure, on the electroplated waveguide structure. So we spin coated PGMEA on top of the waveguide structure, so on top of this steel substrate. And then we performed electron beam lithography, and we did an etching or a stripping process regarding lift-off or the IBE etching. So therefore we could create very small structures on top of a steel substrate or even on the nickel substrates, nickel structures. In this picture, you can see the optical quality of our gratings. You can see the diffraction in these pictures. You can see the different colors. And this picture shows the large gratings we created, still using common lithography processes, using UV light. These structures are at a diameter of 2 micrometers, but also we already can show optical qualities. An interesting question in this case is we use a composite polymer material regarding the laser direct structurable peak. This material has particles inside its polymer matrix for the laser direct structuring. These particles are in between 1 to 5 micrometers diameter, therefore creating a surface with a high surface quality of roughnesses below 30 nanometers for optical purposes is hard to achieve. And even imprinting the optical gratings in these surfaces is even a tougher challenge. But at the Institute, we could create optical grating structures on the peak substrates for optical passive components. In the next step, we did not just look at 2 micrometer gratings, we also tried the ion beam lithography, as mentioned before, electron beam lithography, as mentioned before. And in this picture, you can see that we've created grating structures in ranges between 200 to 300 nanometer width. These grating structures are for coupling light into the waveguide at visible wavelength. These grating structures could be performed on the steel substrate and on the nickel substrate. Therefore, these gratings are possible to implement in the manufacturing process for the optical platform Phoenix D. All right, let's get to the summary and to the outlook. We reached the goal to create a polymer-based substrate for the Phoenix D optical components platform. This polymer platform was based on the laser direct structurable polyether-ether ketone and could be manufactured using the injection molding techniques. We created surface roughness on the electroplated structures on the steels, on different steel substrates, stainless steel or low alloy steel, for the waveguide channels. Different diameters could be fabricated with different aspect ratios. It could be said that aspect ratios of 1:1 can always be performed, and even higher aspect ratios in terms of very thin and high structures of even 1:5 could be achieved, but are not reproducible. So therefore, we say the aspect ratio of 1:1 can be fabricated, definitely. We could fill all the waveguide cavities, which has been imprinted in the polymer substrate. The filling could be performed using the Dr. Blake process and the spin coating process. The surface quality of the waveguide material is, as expected, better than the peak substrate and can be used for the waveguides and optical signal transferring. A very interesting part was the grating structures, which could be manufactured on the steel inlay and could be transferred into the polymer, into the composite polymer material, even though particles of up to 5 micrometer diameters are inside the polymer matrix of the peak substrate. If it comes to the outlook, we can see a lot of potential for optical networks inside the laser direct structural substrate. The thermal and electrical infrastructure can completely be done by the laser direct structuring of the material. Therefore, the platform is the ideal substrate for such an integrated optical components concept addressed in the research project. The platform is very well adaptable for various applications, as therefore only the master tool or only the mold inlay has to be adapted, and mold inlay manufacturing can be performed at the Institute very easily in a very short time. I thank you very much for your attention, and I would love to hear a lot of questions, and you can or feel free to contact me via email, as you can see on slide 1. Here are my references, and on the last slide I want to thank the Cluster of Excellence, Phoenix D, Photonics, Optics and Engineering across innovation across disciplines.
Hello everyone, my name is Shenzhen Zhou from Tsinghua University. The topic of my presentation is a design and fabrication of transmission line for EC4 in millimeter wave applications. Here is the outline of my presentation. The first is introduction. We will talk about 5th generation evolution, package for millimeter wave device, and EC4 for millimeter wave device. As shown in Figure 1, recently 5th generation has attracted extensive interests in many fields, characterized by high speed and abundant spectrum resource. Millimeter wave technology is one of fundamental technologies supporting 5th generation evolution. Millimeter wave device has been widely used, such as smartphone, wireless network device, automotive radar, and so on. The typical package for millimeter wave device is flip chip ball grid array. In such package, substrate such as low temperature coal-fired ceramic or organic are widely used. They are usually thick, hard to miniaturization, inevitably leading to long interconnection paths and high loss. What's more, because of low precision, such package methods face great challenges in millimeter wave device. Known as small dimensions, low cost, and short interconnection paths, fan-out wafer level package has been employed. However, in traditional fan-out package with molding compound, warpage problem is a great challenge due to coefficient of thermal expansion difference of chip and molding compound. To solve this problem, embedded silicon fan-out technology proposed by Daquanyu et al. Is one of the potential solutions. EC4 technology uses silicon substrate to embed chips. Since coefficient of thermal expansion of dies is the same as silicon substrate, there is little warpage problem. In addition, to realize 3-dimension integration, in fan-out wafer level package, traditionally through-mold via is made, which is expensive and rough in dimension. However, the fan-out area in EC4 package is silicon, so through-silicon vias can be easily integrated, realizing high-density vertical interconnection. However, the silicon substrate is usually of low resistance, leading to high dielectrical loss and poor system performance. So the problem is how to reduce the effect of silicon substrate on millimeter wave signal. To solve this problem, from a perspective of structural improvement, a shield line is designed to protect commonly used coplanar waveguide for horizontal interconnection. Meanwhile, a coaxial through-silicon via structure is employed for vertical interconnection. The vertical signal is surrounded by a ground shield wall to suppress undesirable substrate influence. This transmission line design avoids expensive high-resistance silicon and takes full advantage of its CFO technology in high frequency. In this work, we designed a low-loss transmission line for 3-dimension ECFO. Then we analyzed the loss performance using both finite element method and equivalent circuit method. Also, adjacent coupling performance is discussed for high-density applications. 3 different structures are compared: coplanar waveguide with 300 nanometer silicon dioxide layer, and coplanar waveguide with shield line. At last, coplanar waveguide with shield line is fabricated through silicon process and tested by Agilent network analyzer from 1 MHz to 40 GHz. Secondly, let's see the structure of transmission line. Figure 4 is a schematic view of the whole 3-dimension embedded silicon fan-out package. Chip 1 and Chip 2 are micrometer wave chips. Chip 1 is embedded in silicon substrate. Chip 2 is stacked on the top and connected with Chip 1 through a transmission via, consisting of a coaxial through-silicon via and a coplanar waveguide with shield line. To get a better view, we enlarge the connection in Figure 3. We can see the shield line is just between the signal line of coplanar waveguide and the silicon substrate. It's an isolator to reduce energy leakage and decrease dielectric loss of silicon. As seen in Figure 3, the shield line can easily connected with the coaxial ground wall. Now let's see the vertical connection, coaxial through silicon via. The center copper plug is for signal, and the outside wall is ground. Compared with ground signal ground through silicon via connection, due to the surrounding ground isolator, coaxial through silicon via can suppress undesirable silicon substrate loss. Besides, the coaxial through silicon via is easy to realize impedance matching. Thus, is applied for vertical low-loss interconnect in this work. In addition, the green part of Figure 4 is BCB. It is filled in the coaxial through silicon via and coated on both sides of the silicon substrate due to its low-loss property. BCB is also the polymer for redistribution layer fabrication and filled in the small gap between the chip and between the die and the side wall of the cavity on silicon for the convenience of process. To prove the validity of this transmission line, we build a model of traditional coplanar waveguide and a coplanar waveguide with shield line. Figure 6 also shows the location of the shield line more clearly. And we can see that it can be interconnected with the ground wall of the coaxial TSV simultaneously. From the front view, the module has 8 micrometer BCB layer, 5 micrometer copper layer, and a 10 micrometer second BCB layer. These values refer to the process parameters of redistribution layer. Besides, the line width and space is 10 micrometer. From the top view, the diameter of the signal and outside ground are 9 micrometer and 36 micrometer respectively. These values are based on the software TX line and optimized through simulation. As shown in Figure 5, both modules have an area of 1 mm multiple 1 mm on a silicon substrate with 100 micrometer height. The dimensions of the module is summed up in Table 1. The material parameter can be checked in Table 2. We set the thickness of the shield line as a variable for further analysis. Next, let's see the performance of this structure. First, transmission loss analysis. Return loss and insertion loss are essential electrical properties in transmission line performance analysis. In Figure 7, the usual coplanar waveguide is black, and the red is coplanar waveguide with shield line. The left ordinate shows the return loss. It shows that both models is below -15 dB in the frequency range from 10 GHz to 60 GHz. This indicates the impedance of the designed transmission line is close to 50 ohm. Then let's see the insertion loss from the right ordinate. It's shown that the value of insertion loss decreased from -1.6 dB to -0.3 dB at 60 GHz. This indicates the coplanar waveguide with shield line is less lossy than the coplanar waveguide without shield line. Especially, such improvement is more obvious in high frequency. To explain the results shown in Figure 7, finite element analysis, also called field method, is used. From simulation results in Figure 8, the electric field intensity distribution in the silicon substrate is presented, as seen in Picture 8a. The problem of energy leakage is serious. In contrast, in Figure B, there is little leakage in silicon after the use of shield line. It proves the shield line reduced the leakage of electromagnetic waves into silicon. Also, theoretical analysis or circuit method is used. According to transmission line theory, the attenuation constant represents the transmission loss or insertion loss. The attenuation constant is related to equivalent resistance, equivalent conductance, and characteristic impedance of the line. Equivalent resistance is determined by the resistance loss of the conductor itself, and equivalent conductance is determined by the dielectric loss. ZC is characteristic impedance, which is designed as 50 ohm in our work. Figure 9 is an equivalent circuit model of a unit of regular coplanar waveguide. The resistance R1, R2, and inductance L1 and L2 is caused by the conductor itself after taking skin effect into account. Capacitance C1 is caused by coupling between signal line and silicon substrate or signal line and ground line. C2 and G1 represent capacitance and conductance effect of silicon substrate. After adding the shield line, it reduces the capacitance and conductance effect of silicon substrate. So, equivalent conductance GT is decreased. Also, it brings resistors in series, decreasing the equivalent resistance RT. To sum up, the transmission loss is decreased. We add a shield line to improve the performance. But how thick of the shield line is effective? To answer this question, we set a variable of thickness to analysis. The variable was also mentioned in section 2 above. In figure 11, the x-coordinate is the thickness, and the y-coordinate is the insertion loss. It can be concluded that when the thickness of the copper shield line achieves 1 nanometer or above, the performance improves slowly. So we can conclude that when the thickness is above 100 nanometer, it is already effective. These results also give instructions for our fabrication process. That's to say, the thin thickness of copper fabricated by sputtering is enough for performance improvement. After transmission loss analysis, let's see another important issue: adjacent coupling. It's important in high-density applications. A model of two adjacent lines are shown in Fig 12. Fig 12a is two coplanar waveguides showing a same ground line. Fig 12b adds a 300 nanometer silicon dioxide layer between the coplanar waveguide and the silicon. Fig 12c adds shield lines. The result is shown in Figure 13. S parameters from port 1 to port 4 reflect far-end crosstalk. During the frequency range, the red circular curve, coplanar waveguide, acts worst in anti-interference simulation. Only has an isolation of -25 dB at 60 GHz. The black square curve, coplanar waveguide with silicon dioxide, we can conclude they are almost coincide. We can conclude that though previous research has shown that silicon dioxide as an isolation layer can reduce the loss of silicon substrate, it seems helpless in development of adjacent coupling. The green triangle curve, coplanar waveguide with shield line, exhibits an isolation of -48 dB in high frequency. It decreases nearly 20 dB from 20 GHz to 60 GHz. So we can conclude that the shield line is also of great efficiency in dealing with adjacent coupling problem, greatly enhancing the isolation between ports. It can also be inferred that with shield line, it has a lot of application space in high-density occasions. Then we fabricate the coplanar waveguide with shield line, because in the simulation model, the difference of two structures is only the shield line. We just make the horizon line and remove the coaxial through silicon via. The fabrication process of the coplanar waveguide with shield line is described in Figure 14. It is compatible with semiconductor process. Figure 15 is the test wafer, and Figure 16 shows the test platform. These transmission lines are measured by Agilent network analyzer. The measurement frequency ranges from 10 MHz to 40 GHz. Multiple tests were carried out to get the average date. Figure 17 and Figure 18 shows the results of return loss and insertion loss respectively. In Figure 17, coplanar waveguide with shield line shows better stability of impedance matching. In Figure 18, coplanar waveguide with shield line exhibits less loss as insertion loss improves from minus 1.2 dB to minus 0.7 dB at 40 GHz. It also proves that with the growth of frequency, such improvement will be more important in loss control. Besides, the measured results are basically consistent with the simulation result, and the deviation may come from process bias. The final part is the conclusion. In conclusion, the work can be summarized as the following parts. First, the simulation results show that with shield line, insertion loss of the whole transmission line is reduced from minus 1.6 dB to minus 0.3 dB at 60 GHz. Because the shield line and ground wall reduce energy leakage, impressively reducing dielectric loss. Second, the crosstalk problem is alleviated during interesting frequency. High isolation is realized as S-parameter from port 1 to port 4 improves from minus 25 dB to minus 48 dB. Third, the manufacturing of the shield line is simple, compatible with common silicon process, and avoids superfluous steps in fabrication. Finally, this method proves lots of advantages for three-dimension EC4 millimeter wave package. It could be one of the appropriate solutions for millimeter wave system integration to meet the tendency of miniaturization, high performance, and increased component density.
Hi, my name is Jisoo Hwang. Today, I'm gonna share you about power integrity enhancement using MIM capacitor. Start from the introduction. I will introduce you about PDN analysis methodology that I used. After that, we will focus on the effect of MIM capacitor on PI enhancement. The result will be covered by simulation and measurement result. Since neuromorphic computing cores like NPU in mobile phones require an energy-efficient computing, the importance of reducing power consumption and improving PI under low power condition is increasing day by day. However, it is very important to have a small size for mobile devices. Naturally, this leads to constraints on the use of the devices to improve power integrity. To improve PI performance, reducing the peak of the system level PDN impedance is very important. To do so, decreasing the inductance of the package and increasing the on-die capacitance are the keys. Let's find how to do that. In order to analyze the PDN impedance of the entire mobile set system as in Figure 1, PMIC to on-die CPM have to be needed, including board PDN model and package PDN model. First, from the targeted consuming power and operating current level, target impedance can be calculated. The obtained target impedance becomes the standard for the PDN impedance of the entire system, and the design is carried out to lower the impedance as in Figure 2. As in Figure 3, this process is repeated until the impedance is lower than the target impedance. optimal PI, the least expensive and fundamental solution is the optimization of PDN design. It is efficient and fundamental solution for both time and money. There are few important things to consider when designing off-chip PDN for superior PI performance, as stated below. In addition to well designing PDN, one of the most popular methods for designing PDNs with good PI characteristic is to properly place the decoupling capacitors throughout the PDN. When it comes to package PDN, decoupling capacitor can be placed on substrate or bottom board end or in package substrate. Figure 4 shows conceptual description of MIM structure, and Figure 5 shows embedded LICC in package substrate. To analyze system-level PI performance of various combinations of dip caps, we compared 3 cases with respect to PCB embedded LICC and bare MIM. The system-level PDN impedance simulation result, voltage drop and voltage ripple simulation and measurement result will be seen for each PDN cases in this page and later on. Case 1 has no package embedded LICC and bare MIM. Case 2 has package embedded LICC only, and case 3 uses the same package substrate as case 2 and adds MIM. So both LICC and MIM are applied. Table 1 summarizes the application of decoupling capacitor to improve the PI characteristic of each case. It shows that having LICC and MIM both can improve PI performance most. As a result of the time domain simulation, the voltage drop and voltage ripple for each case when the operation scenario is applied are shown in figure 6. Case 2 with embedded LICC has a voltage drop of 24 mV and a voltage ripple of 36 mV less than case 1. Case 3 with MIM added to case 2 has a voltage drop of 24 mV and a voltage ripple of 57 mV lower than case 2. As a result of the frequency domain simulation, system-level PDN impedance simulation result can be seen in figure 7. You can see that case 3 has the lowest impedance and case 2 follows. The PI improvement effect of MIM can also be found by the measurement result in figure 8. As can be seen from both measurement results, case 3 with MIM has less high frequency component than case 2. These measurement results are correlated to the simulation result before. As shown in figure 4, the MIM has to be connected to power and ground mesh through vias, which leads to a density problem that cannot cover the entire chip area. So we analyzed the effect of MIM density on PI performance. For the analysis, the relative MIM density is based on the chip area and swept at 20% interval from 0% to 100%. Table 2 and Figure 9 shows the analysis result of PDN with package embedded LICC and MIM. As can be seen both Table 2 and Figure 9, the higher the MIM density, the better the frequency domain and time domain characteristics. As shown in Figure 10, the degree of effect of MIM density tends to saturate, but for PI improvement, relative density of MIM to its core area is recommended to be more than 60%. In this paper, the effect of MIM in bare region on PI performance is analyzed. Prior to the use of MIM,
We'll present to you our work on flexible batteries under dynamic folding and flex to install with varying C rates and temperatures. The work primarily pertains to flexible batteries. And the performance characteristics that they would exhibit under stresses of daily motion and various variable applications or applications that involve installation of these power sources onto critical infrastructure. from an objective standpoint, the study focuses on the development of a universal life prediction model. We want to be able to assess the amount of damage and the amount of remaining useful. Life in terms of a capacity degradation of the battery itself, specifically in our case a lithium ion source. We'll study the combined effects of accelerated life testing, the impact of using various C-rays the impact of the depth of charge and flex to install or dynamic flexing and we'll look at the impact of various fold orientations specifically the two that we'll talk about in this particular paper are longitudinal fold and transverse fold. And using the various parameters that that are discussed on this particular slide, we want to be able to compute what is the expected battery life in terms of either capacity or state of health using statistical data. So if one looks at a number of different power sources that there are quite a few choices. And if one tries to compare them in terms of specific power and specific energy. Well, there are two different extremes. There are some power sources that will provide you very high specific power, but low specific energy. So, for example, SMES, which is superconducting magnetic energy storage. Provides you high specific power, but low specific energy. On the at the other extreme is TES, or thermal energy storage system. Which provides you high specific energy but low specific power.
Hello, everybody. My name is Kohei Tatsumi, Waseda University, Japan. Here are listed two co-authors of Waseda University, Kyushu Institute of Technology, and Kita-Kyushu Foundation for the Advancement of Industry, Science, and Technology. Here I'll talk about embedded SiC module with using NMPB interconnection for chevron-shaped copper lead and electrodes. Outline of my talk is the following. Firstly, introduction. Secondly, nickel microplating bonding, NMPB. Thirdly, embedded SiC module with using NMPB interconnection, followed by IV and switching characteristics of the module. Finally, conclusions. In order to improve the performance of inverters, the development of new power modules that can increase the output density using technologies such as silicon carbide devices has been progressing. In addition, since these wide bandgap semiconductors can be operated at high temperatures, demand for higher heat resistance of device packaging have been increasing. There are high expectations for SiC devices which enable reduction in size, weight, and the cost of power control units in electric vehicles and hybrid electric vehicles. One of the purposes of the application of high temperature resistance SiC devices is to reduce the number of the chips in power modules by applying high power current density, resulting in increasing junction temperature. This slide shows materials requirements for high temperature packaging. The left figure shows a conventional power device module packaging, and the right figure shows a double-sided cooling packaging used for recent hybrid EV inverter systems. In both cases, The chips are bonded to the substrate by using solder, and the chip pads are connected to the substrate with aluminum thick bonding wires. To realize the high temperature reliable interconnection, the high temperature resistant materials need to be selected and connected at relatively lower temperature, namely bonding is done at lower temperature, but the bond, when done, is stable up to higher temperature. There are several possible methods for high temperature resistance materials considered, but mostly still under development for practical use. The right lower figure shows the melting point of the interconnection materials plotted in y-axis and for their bonding or reflow process temperature in x-axis. We have been proposing nickel microplating bonding, which is processed around 55 degrees C for the materials in nickel of melting point over 1400 degrees C. Nickel was selected as an interconnection material since nickel exhibits relatively lower electrical resistivity, excellent corrosion resistance, and thermal stability. The high temperature reliability and excellent switching characteristics of the one-deck SiC module could be successfully demonstrated. As shown in right figure of this slide, we propose a unique bonding method, nickel microplating bonding (NMPB), applied for plastic SiC power package of double-sided cooling structure and presented at ECTC 2019 last year. Nickel was deposited by electroplating for the interconnection at around 55 degrees C. As shown in this figure, the SiC chips were sandwiched between two lead frames and directly connected to the chevron-shaped top portion of the leads, which enables the interconnection in a narrow gap by nickel electroplating. So this lead frame type NMPB SiC module exhibited the superior thermal reliability in power cycle test as well as thermal cycle test. So this figure shows an example of the power cycle test results. The purpose of this study is to realize prototype smaller and higher performance of SiC power module by applying more simplified NMPB process and structure for an embedded package using an originally designed ceramic substrate and copper leads formed in a chevron shape. Compared with the conventional embedded power modules or the power overlay packages, this technology is advantageous in application to high power devices and simplifying the packaging process. This method can eliminate the lithography, sputtering, and long-term additive deposition process for forming the interconnection. So we designed a SiC embedded module for one leg circuit as shown in the lower left figure. The upper figure shows a cross-sectional illustration of the module embedded in a ceramic substrate. Two pairs of SiC, MOS-FET and SBD, were embedded in device holes formed in the ceramic substrate, having 0.5 millimeter thick copper patterning plate bonded to both sides of the ceramic plate. The lower figure shows a top view of chips and copper leads set and fixed in device holes over ceramic substrate for NMPB process. This figure shows the process flow for embedded NMPB SiC module. The SiC chips are first fixed in the device holes. One edge of the copper lead pressed into a chevron shape is contacted with the surface of the SiC gate electrode, and the other edge surface of leads are contacted with each source and drain electrodes of the SiC chips. Then all the lead parts were fixed using a jig. A bond set of leads, chips, and ceramic substrate with copper plate is placed in a nickel plating bath and simultaneously interconnected by nickel electroplating. The left figures in this slide show the appearance of SiC, MOS-FET, and SBD, and their specifications. Light figures show the ceramics active metal brazing substrate manufactured by Kyocera used in this study. In our previous work, we have identified optimal conditions for NMPB, such as the angles of the chevron-shaped copper leads, electroplating conditions, and so on. For the nickel electroplating, we used a sulfuric acid bath with some additive agent. The plating solution was specially prepared by Japan Pure Chemical Corporation for high-speed plating in the narrow gap between copper leads and chip electrodes. The bath temperature was controlled at 55 degrees C, and the typical plating current density was 1.5 amperes per square decimeter. The left figures in this slide show schematic illustration for the portions of interconnections copper leads to chip electrodes. So designated with AA cross-section, and the copper leads copper patterning plate designated with BB cross-section. Light figures show the optical micrographs for AA cross-section in the upper figure and BB cross-section in lower figures, respectively. So this figure shows the enlarged view of the cross-sections of the interconnection copper lead to SiC chip electrodes, namely AA. There is no significant failures observed in the narrow gap between copper leads and SiC chip electrodes for both source and drain side. The top surface of the aluminum electrodes of SiC chips is coated with electroless nickel deposition of 4 micron in thickness separately. These figures show the microstructure of the electroplated bonds, which is analyzed by using SEM and EBSD. It shows that the crystal grains of bond portion in the gap between copper lead and SiC chip are mostly formed by the columnar rows having 001 or crystallographic orientation. So red color from each surface. The direction of the crystal growth are shown by the white arrow in the figure. In our previous work, it has been clarified that the deposition of the nickel electroplating needs to be performed by crystal columnar grain growth having preferred crystal orientation to obtain the reliable interconnection. It can be suggested from this microstructure analysis that the bond interface is reliable. The other ends of the copper leads need to be connected with the copper patterning the plate simultaneously by NMPB in the nickel plating bath, namely the bonding of copper to copper. This figure shows an example of the cross-sections observation of the bond. The bond is formed also mostly by the columnar growth of nickel deposition as shown in the right SEM back scattering images. IV characteristics of the prototype module were evaluated. This figure shows the IV characteristics and leak test up to 600 volts for the upper and lower arms of prototype NMPB one-leg module. There was no unusual behavior found. the characteristics were confirmed to be almost equivalent to those of the pair chip measure. This figure shows an example of the high temperature operation test. The IV curves of the SIC SPD of the embedded module were obtained at elevated various temperatures. The results show that there is no interconnection failures found. This indicates that the NMPB embedded module can be expected to be used up to 200 degrees C or more. Switching waveforms were measured with an input voltage 650 volts and a current of 100 ampere. The left figure showed
Hello everyone, thanks for your attention for my work. Here I will introduce my ECTC work, design, fabrication, and the characterization of Q-band patch antenna integrated on stacked interposer. This work focuses on antenna in package. Here is the presentation catalog. It consists of 6 parts, including the simulation process and the test result. Here is the background part. In 2020, 5G has come in our life. The antenna working at a higher frequency will have chip level size, so the antenna integration in chip scale is possible. The developed package technology like PCB and LTCC have disadvantages in size and precision. As for EM problem, the fan-out V4 level package is an effective solution, but it will consume more area. For 3D integration with logic IC, the material and the process of radio frequency IC need to be changed to solve the integration problems. The TSV and the process based on the silicon substrate is a good solution for this. Here is some published works about antenna in package. The PCB and LTCC integration have bigger size. As for advanced 3D integration, the Research Triangle Park in the US published a patch antenna working at 94 GHz, integrated on the glass. This antenna has a multi-metallization level glass substrate vertically, which includes a radio frequency interposer and a patch antenna, and the silicon germanium BiCMOS beamformer chip is integrated under the antenna. The antenna structure we proposed is shown. It is integrated on the silicon interposer. The patch is on the upper substrate, fed by the TSV with microbump and CPW, which is on the second substrate. The cavity is designed to improve the performance. The design parameters are shown in the table. The antenna design is simulated in ANSYS HFSS. The simulation results include the reflection coefficient of -27 decibels at 33.08 GHz, a bandwidth of 0.98 GHz, matching efficiency of 99.8% and a gain pattern of 5 decibels. The main process include wafer polishing as figure A, TSV etching as figure B, oxidation as figure C, seed layer sputtered as figure D, copper and tin metallization as figure E, F, and G, and bonding as figure H. Figure A and B shows the photo of fabricated bonding region for vertically aligned wires. One is located at the bottom surface of top silicon interposer. The other is located on the top surface of bottom silicon interposer. Figure G and H are X-ray photos of the patch antenna after removal of seed layer. Before bonding, it can be found a cavity underlying the patch with a wire fed in near the center. Figure C, D, E, and F are photos of the top and bottom substrate of the antenna sample before bonding. The important thing to note here is that we need to ensure a good alignment between the feed wires located as top and bottom silicon interposer. Figure I and G are a pair of photos showing the fabricated patch antenna viewed from both sides. The outline size of a single antenna is 10 mm x 10 mm. For measurement, the vehicle is connected to the VNA by a fixture. It includes a PCB board made of Rhodes 5880, a SMA connector, and a bonding wire. As the figure shows, the vehicle is mounted on the PCB board and connected by the bonding wire. The reflection coefficient is tested by the vector network analyzer. The gain and the pattern are tested in anechoic chamber. After measurement, the working frequency is 32.75 GHz. The bandwidth is 1.04 GHz. The reflection coefficient is -14 decibels. The matching efficiency is 96%. The table shows the result difference between the simulation and the test. About the deviation, we think it mainly resulted by size errors and test fixture. The size errors is cumulative with every lithography. The lateral etching in DRE process leads the bigger diameter of the wire. The effect of test fixture is that the bonding structure between antenna and fixture doesn't match the 50 ohm impedance. After the test, we compare the results with other published works. These works are fabricated on the silicon by 2D or 3D integration technology. This work is comparable in target of size and gain. In conclusion, we introduce a Q-band bicavity patch antenna integrated on the stacked high resistivity silicon interposer. The